All right, everybody. Hope everyone had a good weekend. We're going to, before we get into today's lecture, we're going to do a little bit of review over some stuff that you talked about on Friday. And I have uploaded the 14.1 to YouTube with my voice. So I actually went through and recorded a lecture just in case you want to go back and hear some of them. So we're starting to talk about aromaticity in this particular chapter. So define for me, in general terms, what it means, the term aromaticity. What does that mean?
Aromatic.
And what does that mean? Can't use a word to define a word. Well, those are criteria. Those are specifics. But what does it mean to be aromatic? Just because you can identify the criteria for aromaticity, which we'll do in 2, doesn't mean you really know what aromaticity means. Not necessarily. Certainly true in the case of benzene. What does it mean? What characteristic are we looking at when we say something's aromatic? It's not very reactive. Okay, I can give you a lot of things that aren't very reactive that aren't aromatic, but you're on the right track. That is a result of one of the criteria. But I can also give you things that have just as many alternating double and single bonds as benzene that's not aromatic. What does it mean to be aromatic? Okay, that's a result of one of the criteria again. Okay, I can also show you those that aren't aromatic. What does it mean? Let's get to the essence of it. What does it mean to be aromatic? What do you think, Chance? If we look at benzene, we see a bunch of double bonds as we draw it, right? Does it behave like an alkene? Why not? How does an alkene behave? What does an alkene do? It'll do addition chemistry. Will an aromatic ring do that readily? No. So what would you say then that it means to be aromatic? It has unusual stability, right? Remember you looked at the chart where you took an alkene and you hydrogenated it and you got so much heat out, right? And then you took a conjugated diene and you hydrogenated that and you got a little less heat out per alkene due to conjugation, right? But it was a small difference. And then you took benzene and you hydrogenated it and you got a lot of heat out or very little heat out per alkene? Very little heat out per alkene, meaning what? It is more stable than you would have anticipated based on the number of double bonds. It's an unusual stability, okay? And today we're going to talk about why this is important for those of you who are interested in biology. Aromaticity, this unusual stability, is really good for things like DNA and RNA. We'll talk about that a little bit. Now, you all have kind of danced around the fact that there are 4 criteria that must be met for a molecule to be aromatic. Matthew, tell me one of them. 4n plus 2 equal the number of pi electrons, right? That's whose rule? Huckel's rule. All right, very good. That's one criteria. What's another criteria? It must be cyclic. What else? Must be planar. And what else? Conjugated? Is that a word just good enough? Pardon? It has to be completely conjugated within the cycle. Now, based on these criteria, how many do you have to have for something to be aromatic? All of them must be present. Each and every one of them must be present. Okay? If you get 3 out of the 4, you can't say, well, it's 3/4 aromatic. This is an all or nothing. You're either aromatic or you're in some other category. Okay? You have to be planar, you have to be cyclic, you have to be completely conjugated, and you have to satisfy Huckel's rule. Okay? And if you satisfy all 4 of those, then the molecule is aromatic. And the example that we talked about, of course, was benzene. And if you build the model for benzene, you know that it's planar. It is, by definition, cyclic. If we look at it, right, I can start at one carbon and without lifting my marker, go all the way around back to that starting point. Right? It's completely conjugated. It's completely conjugated because each and every one of those carbon atoms within that cycle are sp2 hybridized and have a p orbital, so it's all completely localized or conjugated. And it satisfies Huckel's rule. What's N? Is it the number of carbons? It's just a what? It's just an integer, right? So 4n plus 2 equals, we have 6 pi electrons here, right? So 4n equal 4, or n equal 1. That's not a 4, that's a 1. That satisfies Huckel's rule. N can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on and on and on and on. But it can't be 1.25. It can't be 3/4. It has to be a whole number, right? Including 0. So benzene satisfies these. In fact, it is an aromatic molecule. It's one of the first aromatic molecules that was discovered. Now, we have 6 pi electrons that we have to account in molecular orbitals. How do we determine the energies for those frontier molecular orbitals of benzene? What method do we use? Okay, the inscribed polygon method, also known as the Frost circle. Okay? That's what I like to refer to it as, the Frost circle, or Frost diagram. And how do I do that? What do I do? Draw a circle. Do I draw a circle first? I do. That's what Harry did? Ooh. You could draw the circle first, but that's not how I like to do it. What do you draw first? We draw the molecule, and how do we draw it? We have to have one vertice point straight down. That's the rule, okay? So you draw benzene with one of its vertices pointing straight down. You just draw the shape. You don't have to draw in all the pi electrons. Now you draw the circle around it, and everywhere that circle touches a vertice, that's where you're going to draw an orbital. So basically, if I look at this, I'm going to have an orbital here, 2 here at the same energy, 2 here at the same energy, and then that's my molecular orbitals for benzene, the frontier molecular orbitals for benzene that need to take into account the pi electrons. Okay? How do I fill in the electrons, Gabby? Where do I start? I've got 6 pi electrons that I need to fill in these orbitals now. Where do I start? The lowest one. And I'm going to put how many in here? I'm going to put 2 electrons in here. Now I move up to the next level. Now how do I fill? It is the highest occupied. So I put 1 there. Where do I put the next one? And why do I do that? That's right. It's degenerate. These are of the same energy. And so we half fill until, and then we go back and pair up, right? So now I come back and I notice that below this line, the so-called center of mass, that's below, right? All of those electrons are populated below that line. And so that is the molecular orbital argument for why benzene is so stable. Okay? These aromatic molecules will have closed shells, no single electrons. Okay? So you have these systems like this using the Frost circle diagram. Any questions about that? Okay. It does matter. And why does it matter? What is the bottom one? It's the lowest energy. You're always going to fill the lowest energy first. Right? Electrons are lazy. They will go to the lowest energy state first. So you always fill from lowest to highest. Now up to this point, you've largely been talking about hydrocarbon aromatic molecules. Not all aromatics are pure hydrocarbons. Some of them will have other heteroatoms like oxygen or nitrogen within the rings. And they too are aromatic, and they're very important in biology. Okay? So we're going to talk about those. We're going to talk about aromatic compounds in biochemistry, and we're going to talk about electrophilic aromatic substitution reactions, one of the reactions that aromatic rings readily undergo. Okay? And we'll talk about why aromatic rings can do EAS reactions, but they don't do addition chemistry. Okay? So this will actually get us into the beginning of 15. And whatever we get through today is what is fair game for the test on Friday. We have a review on Wednesday, and I need to schedule an evening session. So give me some time to work that out. Okay? Pardon? You want it right after lab? You just walk straight there, huh? We'll see what we can do. All right, so this is our good friend pyridine. We've talked about pyridine in the past. What do we talk about pyridine? How does it behave? Pardon? You said it, I think. It's not a strong base, but it's a base. It's a reasonably good base, right? But it is an aromatic molecule. If we notice it, it satisfies all 4 criteria. If you build the model, you will find that it is planar. It obviously is cyclic. It is completely conjugated. Does it satisfy Huckel's rule? I just said it was aromatic, so the answer to that question should be yes. Tell me how it satisfies Huckel's rule. It has 6 pi electrons, and that clearly satisfies Huckel's rule. But what about these electrons on the nitrogen? They're not pi electrons. Very good. And if we actually look at the electronic orbital diagram shown here, you can see that the p orbitals are 90 degrees to the orbital that bears the lone pair on nitrogen. These electrons cannot be part of the pi system. So we don't count them. It's not 6, 7, 8 electrons. It's just 6 electrons that are completely conjugated within that pyridine ring. Okay? Has anybody ever worked with pyridine before? It smells like rotten fish because of the nitrogen, whereas benzene kind of really has a pleasant odor, although I wouldn't recommend you inhale benzene. It's a suspected carcinogen. Guys, if you work around pyridine, don't inhale it. Okay? It has a habit of causing impotence, and not a good thing. Okay? How about pyrrole? Notice it's a 5-membered ring with a nitrogen. Does it satisfy all 4 criteria? Yes, it does. So it must be planar. It's completely conjugated. It's cyclic. How are we satisfying Huckel's rule here? I only see 2 double bonds as it's drawn, right? Shouldn't that just be 4 electrons? That's exactly right. The lone pair is in a p orbital. Okay? So this lone pair is in the p orbital, and so we've got 2, 4, 6 pi electrons. That satisfies Huckel's rule. That's the hydrogen that is perpendicular to the pi system. So you have to know where that lone pair is going to be oriented. In things like pyrrole, it's going to be in the plane of the pi system. Okay? If it's in pyridine, it's going to be perpendicular to that plane, and you're going to have to count them differently at different times. Okay? So this is a very aromatic, or not very, I should say, just an aromatic molecule. Okay? If we look at the cycloheptatrienyl system, what you would find is that that molecule readily gives up a hydride. It's a reasonably good hydride donor, H-. What else have we talked about that's a good H- donor? Sodium borohydride. What else? Lithium aluminum hydride. Very good. This is unique because why? Compared to those other hydride donors, what makes this one unique? Pardon? It's purely organic, and you're losing a hydride from a CH bond. Have we seen that happen much? Not at all, right? And so this organic molecule is a little unusual. It readily gives up an H as H minus. And in doing so, because this hydrogen is going to carry with it both electrons in this bond, that leaves a cation here, right? Explain to me, based on aromatic theory, why this is such a good hydride donor. Now we have complete conjugation. We end up with what's known as the tropylium ion. And what do we know about the tropylium ion? Why is it very, very stable? Because now it's aromatic. And so we went from a molecule which was non-aromatic to something that is aromatic. How do you think the equilibrium is going to lie there? To the left or to the right? To the right. Because it's extremely stable, right? The product here is considerably more stable than the starting material. All it's got to do is lose a hydride, and you end up at an aromatic system, okay? It has 6 pi electrons, 2, 4, 6. The cation doesn't count, right? It's empty. And so we can do a frost circle where we take our ring, invert it, draw the circle. We have the orbitals, and we see that below that line we have all 6 of our electrons. And so this is an aromatic system, okay? So we can have hydrocarbons that will do strange things to become aromatic, right? We don't think of taking something like ethane or cyclohexane and getting a hydride from it, right? Doesn't happen. But this hydrocarbon does it because it can become aromatic when it does so. And so the energy becomes much, much lower and much more stable, okay? We can also have hydrocarbons that actually behave in a fashion that is more acidic than you might expect. What's the typical pKa of a typical hydrocarbon? Around 50, right? What's roughly the pKa of an allylic hydrogen? So you got the carbon-carbon double bond, another carbon with a hydrogen on it. Is it more acidic or less acidic than typical hydrocarbon? It's more acidic, that's right. And where would we put the pKa approximately for that? Give me a range. More on the 35 to 40 range. Close enough, okay? But it's lower than what Brian had mentioned for a typical hydrocarbon, right? Because of conjugation, right? Well, it turns out that cyclopentadiene has a pKa of 16. What base would you suspect would be strong enough to remove that hydrogen? What else has a pKa of around 16? Water. So hydroxide should be a strong enough base to deprotonate a hydrocarbon. That's weird, right? Because we normally think of hydrocarbons as having pKa's close to 50, right? But we're a little lower in Gabby's case. But this one is acidic enough that it can be deprotonated by something like sodium or potassium hydroxide. And the reason is, if it loses a proton, you end up with what's known as the cyclopentadienyl anion, which is aromatic, non-aromatic, or anti-aromatic. What do you think? The three of you, I've got this sea of gold back here. My eyes just keep being drawn to it. We need to get Karina to sit back there, and then it'll all be gold. It'll be one gold bar. What do you think, Sarah? Why is it that this is so acidic compared to a regular hydrocarbon? What makes a strong acid strong? The stability of the conjugate base. What's the conjugate base here? An aromatic anion. That's exactly right. So we went from something that is non-aromatic. It's certainly conjugated, right? But conjugation by itself doesn't give us a lot of stability. I mean, it gives us stability, but not as much as being aromatic, right? So if this loses an H plus to the base, it becomes a aromatic anion, and that's extremely stable. We've got all these resonance structures. It is planar. It is completely conjugated. It is cyclic, obviously, and it does satisfy Huckel's rule, because how many pi electrons does it have? has 6. And that satisfies Huckel's rule. Okay? Now compare that to cycloheptatriene, pKa of 36. For all practical purposes, that's double in terms of the scale, right? Of course, we're in a logarithmic scale, so that's a huge, huge difference, right? Explain that to me, Jamie. Why is it that this isn't around 16? Why is this so much higher in pKa? It is not as stable as this one. That is correct, right? Well, shoot, I can draw a bunch of resonance structures. Why isn't it more stable? It doesn't satisfy Huckel's rule. What does it satisfy? If it were planar, it would be anti-aromatic. You're absolutely right. Remember, anti-aromatic is 4n equal the number of pi electrons, cyclic, completely conjugated, and planar. And that means unusually unstable, right? So would you predict, Gabby, that this molecule would be planar or non-planar? It's not going to be planar. That's right. If it becomes planar, it becomes anti-aromatic. So in order to avoid that anti-aromaticity, it puckers. And it doesn't let all of its orbitals conjugate with each other. And so even though we can draw these resonance structures, the fact of the matter is it's not planar. Okay? If it were planar, it would be anti-aromatic, which is extremely unstable. You can do this. pKa of 36 is easy to achieve, but you don't get a aromatic stabilization in the anion, and so this molecule is considerably less acidic than cyclopentadiene. Okay? This particular reaction was one of the first reactions I ever did when I was in my organic class at the University of Arkansas, where we made ferrocene, which is 2 aromatic cyclopentadiene rings with an iron stuck in the middle. And you actually take cyclopentadiene, you freshly crack it so it's fresh, and you treat it with sodium hydroxide. You make the anion, you throw in some iron. Can't remember which iron salt we threw in, iron chloride or something, and you get this nice, beautiful orange organometallic species known as ferrocene. Okay. How many of you are going to go on and take biochemistry? Good chunk of you, right? Good. Many of our amino acids contain aromatic rings. Okay. These are essential. Phenylalanine and tryptophan. What does it mean to be an essential amino acid, Gabby? Definitely need it for sure in our diet because we have no machinery that's capable of synthesizing it ourselves, right? So we have to have a diet that is rich, to some level anyway, in phenylalanine and tryptophan, okay? We cannot synthesize benzene rings. We just don't have the machinery to do it, or aromatic rings. Phenylalanine has a benzene ring in what we call the side chain, so that's an aromatic molecule, okay? Tryptophan, where's the aromatic ring? Is it the whole thing, or is it just the benzene part of it here? It's the whole thing. It's because I looked at you funny. That's good. It's the whole thing. Now tell me why it's the whole thing. Tell me how it satisfies the 4 criteria. Anywhere in the criteria does it say it has to be a single ring? No. It has to be cyclic. Is it cyclic? You bet. I can start at the nitrogen, go all the way around, end up back at nitrogen. So it's cyclic.
But it's not conjugated.
Is it not? Could I not draw resonance structures that push these electrons around the whole ring? There is an sp. This is an sp2 hybridized nitrogen, so there's a p orbital, a p orbital, 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 p orbital. It's completely conjugated. So it's cyclic. It's completely conjugated. Think it's planar? It is planar. Build a model of it, you'll see. Does it satisfy Huckel's rule? equal 10 pi electrons, right? So 4n equal 8, n equal 2. That satisfies Huckel's rule. Tryptophan, the side chain of tryptophan, the whole unit itself is aromatic. The point I want to make here is this just looks like benzene, right? But it's the whole system, okay?
The side chain is
This part, yep.
okay.
Yep. There are also other things that are important. Purine and pyrimidine. These are also aromatic systems. Why are they important? That's exactly right. Why do you suppose nature chose to use an aromatic ring, or aromatic rings, I should say, to store your genetic information? It's stable. It's usually unreactive, right? We do not want a biological code that keeps us going, right, based on an unstable format. All right? You don't want that. Yeah?
Okay, this is just a curiosity question. But earlier you said that benzene rings were like known carcinogens, not but like possible carcinogens.
Mhm.
How come they're essential to our health? Or is it like just it by itself?
Benzene just by itself, pure benzene, is a carcinogen. It's attached to something else. It's no longer just benzene, right? It's a benzene ring, but it is not benzene itself. Yep, good question. Okay. So Mother Nature picked aromatic compounds to store your genetic code so that you can keep that genetic code relatively intact for long periods of time. It's worked very well for us as a species, right? If we had an unstable genetic code, we would have mutations all the time. We already have enough mutations that occur, right? So this is kind of one of those methods of ensuring the longevity of what makes us us, okay, is to use an aromatic system. So it is important. When you all get into biochemistry, you will be talking about the amino acids, and you'll be talking about how they're connected to make proteins or large peptides, okay? And you'll find out that tryptophan and phenylalanine have certain properties, and that's why they're placed in certain positions of an amino acid, okay? Because they're hydrophobic, they're aromatic, they're stable. They can form hydrophobic interactions that help stabilize your secondary structures. You're going to learn all that fun stuff when you get to biochemistry, okay? This is not a real quiz, but using the polygon and circle method, or the Frost method, I want you to predict for me which of the following species is aromatic, non-aromatic, and anti-aromatic. I'll give you about 3 minutes. Aromatic, non-aromatic, and anti-aromatic. Assume all are planar. All right, what do you think about the first one, cyclopentadiene? Okay, so this would be the orbitals, right? And I've got how many electrons? Show me how to fill them.
Bottom one up and down, and then the two ones up and up.
Is that a completely filled shell? No. This is why cyclobutadiene has only been prepared a handful of times at extraordinarily low temperatures, and it only existed for a fleeting moment because it reacts with anything it can because it's got these unpaired spins right there at that point where you would want to have an aromatic molecule. Okay? So, how about the second one? Aromatic, non-aromatic, or anti-aromatic? Aromatic. Why is it aromatic? Okay, that's right. And it satisfies whose rule? Okay. How about the third one? What is it? Is it non-aromatic or anti-aromatic? Why would it be anti? Okay. Huckel's rule, right? So it would satisfy 4n equal the number of pi electrons, right? And how about the last one, cyclopentadiene? We've already done that one, right? It's, Katie? It's aromatic. That's right.
That second one, why are there 3 electrons in there? What is that H plus doing? No A of pi electron?
Now, excuse me, the third one?
The second one, why did we get aromatic for that?
This one?
Yeah.
Because there's 2 electrons.
Okay.
There's a p orbital on every carbon, so it's completely conjugated. It's cyclic. It's planar. 3 points define a plane, right? And so,
3 pi electrons in that?
just 2. That's a cation, right? So there's no lone electrons on that carbon. It's just an empty p orbital. It is aromatic. The next one is anti-aromatic. That's right. Now, you learned on Friday that if you take benzene and you add bromine to it, for example, you will have a solution of bromine in benzene. Bromine will not add across the carbon-carbon double bonds, quote unquote, of benzene. Why does that reaction not occur? Pardon? It is stable. Tell me a little bit more, though. All right, we're going from an aromatic system, which is unusually stable, right, to what? Relatively unstable. Now, it is a conjugated diene, but it's still going uphill, right? So benzenes here, our products here, that's usually not a good thing, right? So I lose my aromaticity in doing this reaction, okay? However, we can do what's known as an electrophilic substitution reaction where we are removing the hydrogen and replacing it with some electrophile. I can do that reaction. Why can I do that reaction? I have in my product an aromatic compound, right? So I'm going from an aromatic system to an aromatic system. So that should be possible, right? I'm not losing my aromaticity overall in the process. There will be an intermediate that I lose the aromaticity in when we look at the mechanism. But the product itself is aromatic. And so we can do what's known as electrophilic aromatic substitution, okay? Were we able to do that type of chemistry with an alkene? What did we do with alkenes? Yeah, we added things across the double bond, right? But it turns out that benzene doesn't like to do this. You can add things to benzene, but it's difficult. That's right, that's right. So like the hydrogenation, right? But nonetheless, we can do these types of things fairly easily, these electrophilic aromatic substitution reactions. These are known as EAS. You need to know that by name. If I say EAS on an exam, you need to know what that means. Okay? Here's some examples of electrophilic aromatic substitution reactions. We can replace the hydrogen with either a chlorine or a bromine through what's known as electrophilic halogenation. Okay? The electrophile will be a positively charged chlorine, and I put that in quotes, or a positively charged bromine in quotes. Okay? The nitration reaction will be replacing the hydrogen of an aromatic ring with a nitro group, NO2. We can replace the hydrogen of an aromatic ring with a sulfonic acid. Okay? We can replace the hydrogen of an aromatic ring with a carbon in what's known as Friedel-Crafts alkylation, after Friedel and Crafts who discovered it. We can also replace the hydrogen of an aromatic ring with a carbonyl group, so making a carbon-carbon bond here, and this is called the Friedel-Crafts acylation, where we're going from an aromatic ring to a ketone. So now you know how to make ketones again. How else have we made ketones in the past? Of what? What type of alcohol? Secondary. So I can oxidize a secondary alcohol to a ketone. I can also make a ketone by ozonolysis of a carbon-carbon double bond. And now I can make a ketone by Friedel-Crafts acylation. Okay? What's so important about these two reactions? I'm forming carbon-carbon bonds. Okay? We're forming carbon-carbon bonds. How else have we formed carbon-carbon bonds? Grignard reaction, so we can add a Grignard to a ketone, or an aldehyde, and we can get a carbon-carbon bond. How else? Another named reaction resulted in a Nobel Prize for two people. Diels-Alder. Any others? We did free radical polymerization in Chapter 10 that made some carbon-carbon bonds, right? There's not many ways. You know a lot of ways to make an alcohol. You know a lot of ways to make a ketone. But you know fewer and fewer ways of making carbon-carbon bonds. And so these are very, very important reactions. Okay? This reaction, the sulfonation reaction, is very, very important to get your clothes clean. This is how you make detergents. They actually make it by the sulfonation of benzene-containing molecules that make surfactants. Okay? So these are important reactions, both industrially as well as academically, to drive you crazy. Okay? So very, very useful types of reactions. There is a general reaction mechanism that we're going to go over. The cool thing is once you've learned the general mechanism, it's easy. Everything else is just small details. So let's look at the general reaction mechanism for the electrophilic aromatic substitution. So we're going to take benzene and we're going to react it with a general electrophile, E+. And of course, there also have to be something like a counterion, right? We're just going to keep it general right now. Sam, what do you suppose the first step is? You tell me. You're in the driver's seat. We're going to do an electrophilic aromatic substitution. So what are we going to replace? And replace it with the electrophile, E+, right? How do you suppose that happens? You think that's going to happen? You think that hydrogen's just going to come off by itself and then... Okay, so how's it going to happen? E+ is what? A Lewis acid or a Lewis base? It's a Lewis acid, right? It's E+. What on benzene could function as a Lewis base? The hydrogen? The pi bonds, that's right. So what happens is the pi bond reacts with E+. And I'm just going to draw one hydrogen in, okay? You end up with a cation that is resonance stabilized. Is that aromatic or non-aromatic or anti-aromatic? What do you think, Gabby? It is non-aromatic. And why do you say it's non-aromatic instead of anti-aromatic?
Because
It doesn't fit all the criteria, right? Certainly it has the 4 n pi electrons, but it is not completely conjugated, is it? It's probably also not actually planar either. Now what happens to get my aromaticity back? How? Very good. So I get some acid HA plus that. Easiest mechanism I've ever shown you probably, right? So what's the trick? No, that's easy. What's the trick? It does actually work like this. What's the trick? The trick is, how do we get E+? Remember I said we get halogen plus, and I put it in quotes? There's never really Cl plus floating around in solution. The trick that you're going to have to figure out is, how do I get my electrophiles? Okay? So, what do I need to get my electrophiles? Let's go back and look. So, to get my chlorine plus or my bromine plus, what do I need? Let's say it's bromination. What do I need? Rose, what am I going to need in the lab to do this? You go into Dr. Wallace's lab and he says, I want you to make bromobenzene out of benzene for me. What are you going to have to go find other than the benzene? Pardon? Aluminum? The top one, halogenation. What are we going to need, Sam? We're going to need iron tribromide, and we're going to need molecular bromine. And that will generate the Br plus for me. And again, that's in quotes. It's not going to really be Br plus. We'll see how that is in just probably next week. Okay? So you need to know you're going to need some type of iron trihalide, and you're going to need your halogen, either chlorine or bromine. What's absent here in terms of the halogens? Fluorine and iodine are not there. You can't do this. Okay? Iodination of benzene is actually not easy, and fluorination goes boom. Okay? So you're limited to chlorinations and brominations. If you were to come to my lab, why would I tell you to do a bromination instead of a chlorination? I might go a little faster. But you're taking my lab for credit, so you got to be in the lab for a while anyway, so I'm not really worried about the time. Chlorine's a gas. Bromine's a liquid. Easier to handle. That's right. What do I need? Pardon? Technically, you could use NBS because it will decompose into bromine slowly. But usually for these reactions, we actually use molecular bromine because NBS does decompose so slowly. Okay? What do I need for nitration? What are the reagents? Sulfuric acid and nitric acid. What do I need for sulfonation? I need sulfuric acid and SO3, which is a gas. If I want to do Friedel-Crafts alkylation, what do I need? You're up, Gabby. I need aluminum trichloride and what else? An alkyl chloride. That's right. And Friedel-Crafts acylation, what do I need? Gabby? I need aluminum trichloride and what else? What's RCOCl? What functional group is that? What do you think, Jamie? What is that? Okay, it's a carbonyl group with a chloride. What do we call that? That looks like a carboxylic acid, but it's instead of an OH here, it's a chlorine. It's an acid chloride. That's right. So we need an acid chloride and aluminum trichloride to get that reaction to go. Okay? These are the conditions that you need to generate these electrophiles. Once you have the electrophile, it just follows the general electrophilic aromatic substitution reaction mechanism, which is easy as cake. Okay?
Is the R group always a hydrocarbon?
Yes. And there will be some little things that we get into when we get further into chapter 15. Okay? There are some rearrangements that are possible in 4. Why would 4 show potential rearrangements? Technically, I can ring expand, but that's getting into a more complicated scenario that I don't want to cover in this class. What typically rearranges? Carbocations. What's my electrophile? A carbocation. So if I generate a secondary carbocation, could that rearrange to a more stable carbocation? Possibly. So what might I expect to see in the Friedel-Crafts alkylation reaction? Rearrangements. Okay, so don't forget about rearrangements when you're looking at these reactions. Okay? This is what the energy diagram sort of looks like for the general electrophilic aromatic substitution reaction. The first step is the slowest step. Why do you suppose the first step is the slowest step, Chance? What do you mean, they? What are we talking about, they? Okay, so we're going from an aromatic ring to what? A non-aromatic intermediate, right? That's got to be higher in energy. So why then is this step, the energy of activation here, so much smaller than the energy of activation of the first step? Okay, this is less stable, and what else? I'm going back to an aromatic system. So the transition state here is going to be pretty shallow. It wants to go back, to give it kind of personality. It kind of wants to go back to an aromatic system, right? And so as long as your product, that new bond that you form between the aromatic ring and the electrophile, stabilizes it and lowers the energy of the system, this reaction is going to go to the left or to the right in terms of equilibrium. It's going to go to the right. These reactions are very, very difficult to screw up. They work almost 100% of the time, very, very well behaved. Okay? Very, very well behaved. So, and in fact, you all will do an electrophilic aromatic substitution in lab. And all of you will get more product than you need to do all of your characterization. And if you don't, yeah, because it's one that you should get. All right? All right, I think I'm going to stop here for today. We've only got a couple of minutes left. So up through this slide, so the general electrophilic aromatic mechanism, what kinds of electrophiles we can work with, all that would be fair game on Friday's test.